Today we're going to talk about different types of rules for sequences. One that we already know was the explicit rule. An explicit rule, as defined by our text, is a rule for a sequence that gives a sub n as a function of the term's position n in a sequence. That sounds really complicated, but all it means is something like this. If I want to know what a sub n is, here's the rule. So I could figure out what a sub whatever is. I could do a sub 3 just by putting in 3 for n. I could do a sub 10. So I get 40. I could do a sub 100. I can do any term that I feel like, and all I have to do is figure out whichever term I want and put that number right here, and that will give me a sub n. I could do a sub 500, a sub 5 million. Doesn't matter, it would be really easy to calculate using this explicit rule. Now there's another rule that's called a recursive rule. Now a recursive rule is defined by our text as a rule for a sequence that gives the beginning term or terms of a sequence and then a recursive equation that tells how a sub n is related to one or more of the preceding terms. That's a really complicated way to say, okay, here is a sub 1. A sub 1 is 5. To get the next term, I want to add 3. So that means that a sub 2 is equal to 5 plus 3, or 8. I can get a sub 3 because I take the 8 and I add 3 to that. I can get a sub 4 by taking the 11 and adding 3. I can get a sub 5 by adding 3. But do you see a problem with this recursive formula? If I want to figure out a sub 100, I need to have a sub 99. In order to get a sub 99, I need to get a sub 98. In order to get that, I need to get a sub 97, and so on and so on. And so in order to get a sub 100, I have to have the first 99 terms. But that is what it is. It's a recursive rule. Here's an example of a recursive rule. Now, I'm starting here with a sub 0. You don't always have to start with a sub 1. So far that's all we've done. But you can start with a sub 0. So in this case, and by the way, this is an example straight out of your book. It's on page 681. It's example 1. A sub 0 is equal to 1, and a sub n is equal to n times a sub n minus 1. This means the term that came just before a sub n. So if a sub n was 5, a sub n was a sub 5, then a sub n minus 1 would be a sub 4. If a sub n was a sub 7, that would mean that a sub n minus 1 is a sub 6. Just means the term that came just directly before a sub n. If I was talking about a sub n minus 2, that would be the term that came to before a sub n. So we're supposed to write the first 5 terms of this sequence. So we're told a sub 0 is equal to 1. That's the first term. My second term is a sub 1, and to get that I need to take n times a sub n minus 1. So take n, which is right here, 1 times the term that came just before this. So 1 times 1 is 1. A sub 2, I'm going to take n, which is 2 now, times the term that came just before. So that would be 2. A sub 3 is my fourth term, and I would take 3 times 2, which is 6. And a sub 4, which is actually my fifth term, is equal to 4 times 6, which is 24. This is the next part of that same example from the book. This is part B. And what we're doing is we're finding a Fibonacci sequence this time. Notice this time they're not just giving us the first term, they're giving us the first two terms. And to calculate a term after that, I need to take the term that came just before that plus the one that came just before that. So let me show you how to find the 5 terms. My first term is given. My second term is given. A sub 3, my third term, is going to be this a sub 1, that's my a sub n minus 2, which would be a sub 1, plus a sub n minus 1, which is also 1. So I get 2. My next term is a sub 4, and I need to take the two terms that came before that, so 1 plus 2. So a sub 4 is 3. And finally a sub 5, take the two terms that came just before a sub 5, which is 3 and 2. So 2 plus 3 is going to give me 5. So these are my first 5 terms of the Fibonacci sequence. Here's another example of a recursive formula. I'm given the first term is 9, and to find a term I need to take the term before it and add 3. So I'm going to find the first 5 terms using this recursive formula. A sub 1 is given. A sub 2, I want to take the term that came just before a sub 2, which would be a sub 1, that's 9, plus 3. So it's 12. A sub 3, I take the term that came just before, and I add 3. The fourth term, I take the third term, add 3, and finally, because I'm supposed to find 5 terms, take the 18 plus 3 gives me 21. Now I hope that you noticed that this is an arithmetic sequence. Each time to get the next term I have to keep adding 3. So 3 is my common difference. If you remember from a section or two ago, if I have an arithmetic sequence, a sub n is equal to a sub 1 plus n minus 1 times d. So if I were to find this is the recursive. If I was to find the explicit formula, this is what I would do. I would use this formula and substitute in what I know. A sub 1 is 9 plus n minus 1 times my common difference of 3. Distribute the 3 and add like terms. So this would be my explicit formula, 6 plus 3n. Here in example 3, I want to find the first 6 terms of the sequence. Now notice that this is written as a recursive definition. So my first 6 terms would be 6. In order to get a sub 2, I need to know a sub 1 first. So that would be 6 minus 3 is 3. A sub 3 would be 3 minus 3. A sub 4 is 0 minus 3. And finally, nope, not finally, this is only a sub 5, is negative 3 minus 3. And then finally, a sub 6 is equal to negative 6 minus 3 is equal to negative 9. Now this is all the recursive formula. And again, just like the last example, this is also arithmetic, with the common difference being a negative 3. If I wanted to write the explicit formula for this, what I need to do is go back to what a sub n is in an arithmetic sequence. So that's a sub 1 plus n minus 1 times my common difference. So a sub n would be 6 plus n minus 1 times my common difference is negative 3. So I just want to simplify this now, and I end up with a sub n is equal to 9 minus 3n, which is my explicit formula for this sequence. Example 4 is really similar to the last two. we need to use this recursive formula to find the first 4 terms. But the difference between this and the last two is that this is a geometric sequence, and I can tell because I'm multiplying by 3 to get the next term. So a sub 1 is equal to negative 2. A sub 2 is equal to negative 2 times 3, which is negative 6. A sub 3 is negative 6 times 3, which is equal to negative 18. And a sub 4 is negative 18 times 3, which is equal to negative 54. This was the recursive rule. Right here that led me to these 4 terms. We can also find a recursive definition for this same sequence, but I need to recognize that it is a geometric sequence this time. So I would have to use this formula. A sub n is equal to a sub 1 times r, which was our common ratio, raised to the n minus 1. So a sub n is equal to negative 2 times my ratio of 3 raised to the n minus 1. And I can simplify this. This means 3 raised to the nth times 3 to the negative 1, because when I multiply with the same base, I add exponents. This exponent of negative 1 means to do the reciprocal. So negative 2 times 3 to the n times 1/3, and that would finally simplify to negative 2/3 times 3 to the nth. And this would be my explicit definition for that same sequence.